In this video, I'm going to be going through the 2014 Preliminary Engineering Studies exam. This is the exam that's taken at the end of Term 3 in Year 11 before we start the HSC course. It assesses everything that we've done up until this point. This was, for context, this was the first year I was teaching, and it's the first prelim exam I've written. There are some things that I would change now, but it's probably a little simpler than tests that I would make now, but let's get going. Okay, so first thing is Young's modulus is the measure of stiffness of materials. So if we go to Young's modulus is, yep. Oh, okay, I did have a different picture I was going to use, but we'll start here. Okay, so Young's modulus is written as the capital E, so Young's modulus of elasticity. Young wasn't the first person to come up with it. I think it was actually Euler, but Euler has so many things named after him that they don't give him the letter. I have this picture of Elastigirl because she was called Elastigirl when she was younger. I have the song Too Young, which I think is a pretty cool song. And going back to Spanish Flea, so Young's modulus is the gradient of the stress-strain diagram. So I'm not sure if this will go to a stress-strain. Nope, it's just a picture of Homer singing Spanish Flea. And yeah, I have a loop of a 1 hour loop of Spanish Flea. So if we go look at a stress-strain diagram, which I'm not sure I'll be able to find quickly and easily at the moment. Oh look, I'll just type in stress-strain diagram. Go with steel, we like to look at steel. So the rise over run is the Young's modulus. So the steeper that gradient, the higher the Young's modulus. It affects things like deflection. It's probably its main thing. Okay, so next thing, we can close these as we go. Oh. Okay, so the next thing we can talk about is cold rolling. Now, it says cold rolling improves strength. Now, it says here you should typically specify what kind of strength, so tensile strength or compressive strength. I have made a big thing recently that's saying you will not get marks if you write the word strong. So keep that really in mind. In terms of rolling, so I mean, I have my story, my Camellia joke about they see me rolling, but if we look at this, we can see rolling. So I always talk about rolling rail for trains and for train tracks, and there is hot and cold rolling, and that is discussed in the year 12 textbook, hot rolling and cold rolling. I don't go into it in that much detail in year 11 because it's not relevant yet. Hold on, that may have been visible and I just didn't see because it's not on my preview. Looks like it was okay. Sorry about that. Okay, so but cold rolling, we have still talked a little bit about work hardening. Oh, before that, this is some hot rolling. I can't normally show this in class because it's on Reddit and Reddit's blocked. But yeah, a bit of a disaster. Too much rolling. They hating. There you go, that's 30 seconds, you're never getting back. Okay, so when we talk about annealing, we talk about work hardening. So when we cold rolling steel hardens it and produces elongated or stressed grains. So if we look at this video, we use this video all the time, properties and structure of grains. We can see that if we roll the steel, we get elongated grains. Those elongated grains have more stress, but they have less toughness, so that's the payoff. So if we want to reduce that, if we want to take away the stress, we can anneal, and that will relax the stress. If we hot roll, it's kind of like annealing at the same time, but it has some downsides. It has some upsides, but it has some downsides. Okay, so next thing we're going to talk about is double insulation. And so I don't know, have earth wiring in my mind. I was going to talk about earth wiring. I guess maybe with some other point we'll come back to earth wiring and that will make sense. But double insulation, well, I guess this is relevant. So yes, that is relevant. Okay, so when we have in Australia, or our appliances have, not all of our outlets have 3 pins. The yellow and green pin goes to an earth pipe, but not every appliance uses that. So we have 2-prong and 3-prong devices. If we have double insulation, we only need 2 prongs, but if not, it needs to be earthed. So that will be that. Okay, perlite is a lamella, which is a layered mixture of cementite and ferrite. So if we look at this, this is my diagram for iron carbon diagram. This is not actually accessible exactly, the diagram, but it's pretty useful. And perlite is when we have layers of ferrite and cementite. Okay, so when 0.6% carbon steel is heated to over 900 degrees, so till red hot, or gamma steel or austenite, and then quenched in oil, martensite is formed. Okay, so if we heat up to this yellow zone, right, so if we hit, so we said 0.9 is heated up till 900 degrees, and then it's cooled rapidly, what will that be? Well, that will be this one here. So we're going to heat to austenite, or heat to 100% gamma steel. We're going to cool by quenching it rapidly in oil. We're going to get acicular martensite, which is brittle. Martensite looks like this. It's, when we draw it, we just draw it like lines, just to show needle-like. Acicular means needle-like. Yeah, so martensite is what's formed. The combination that has the highest friction is rubber on rubber. So I might come back to this because there's a lot of stuff on heat treatment in year 11. Okay, so in my video on brakes part 2 mechanical, I talk fairly extensively about different coefficients of friction, and I think I talk about rubber on rubber being pretty high. Platinum on platinum is actually really high, but what do we talk? Where do we talk about that in the textbook? So on page 95, yeah, on page 95 we talk about different values that we should be familiar with. And it doesn't actually list rubber on rubber, but rubber on rubber is indeed higher, the highest of those options. So moving on to when an object is raised from the ground and released, it is kinetic, potential energy to kinetic is what happens. So if we go to back to our videos and things, we're done with that. Okay, so you might remember the Eureka videos that we sort of introduced right back when we started. And in this series here, they talk about work and energy. Work. I could have got like the unit of energy being joules, because Drake, he's all about joules. And there we go, Drake's all about joules. He doesn't like calories. And so right at the start of this, I think they talk about if there was a big rock. Oh no, we haven't. So we do work. So work is the energy is the ability to do work, and then they talk about if you wouldn't stand under a rock, because that'd be bad, because we're potential to do energy. Okay, so I'm sure Crash Course has a great video on that as well. Okay, so we can move on, and surely love is the greatest force of all. Anyway, what do we got next? We've got, okay, orders of levers. So we've got this video here, I talk briefly about the orders of levers, and when we calculate mechanical advantage and things. But orders of levers is here. So we have the 3 orders of levers, first, second, and third. I don't know why I didn't have, I guess, that picture. I guess I felt as I was already in the video. So I have this picture here. It's got a couple of examples of different orders of levers. The classic first order lever is a seesaw. That's where you have the fulcrum in the middle. The second order lever, so the first order lever can have a mechanical advantage either above or below 1. The mechanical advantage, second order lever always has a velocity ratio greater than 1. And I always think of this as a wheelbarrow carrying number 2s. So it's filled with, manure. And the load of number 2 is near the wheel. And then the third order lever, I always use the example of a fishing rod, but sugar tongs or tweezers are a good example as well. And the idea there is that they'll have a mechanical advantage less than 1, which is why the fish feels heavy when you're bringing in the fishing line. It actually feels heavier than it should. And the reason we do this is because the advantage we're getting is that we want, the advantage we're getting is the reach, or in the case of tweezers, the precision. So back to the notes. And I just don't want that elephant in the background forever. Oh no, it's going to be in the background forever. Well, not forever. Forever. Okay, so we're into drawing standards next. Okay. Oh, okay. Aeroplanes are designed to have a lower factor of safety than other vehicles because they have strict servicing requirements. Yeah, I said here that the wording of this question is vague. I would have also marked A as correct. I think A was that planes need to be light. So that was a question I used in this year's Year 12 question. I probably wouldn't put this in a I wouldn't put this in the Year 11 test anymore. Okay. The next thing is drawing standards. And so what you've been asked to do is you've been now asked to determine the thickness of a bolt, or this dimension of the head of a bolt. And we've said that it's 0.7 times the major diameter. So the major diameter is that diameter. And that is the number. So if we have an M30 bolt, M30 is that diameter, the major diameter, is 30. And so if we multiply that by 0.7, we get 21. This is a tough one. It's not in the Year 11 Copeland book. It's in the Year 12 Copeland book on page 64. I have that here. I have gone through that with, and I do go through that with Year 11s. The reason why I go through that with Year 11s more than anything is because these sorts of questions are asked a lot when we get external exams. Sometimes I tend to write the exams. I have since I first started teaching in 2014, but when we look at external exams, that's the sort of questions very commonly in external exams, and it's not really clear in the syllabus what is accessible, or what is accessible, sorry, in Year 11. Okay, so we have the best description of engineering management. Yeah, the efficient utilization of labor and resources to achieve project outcomes. Yeah, it's I mean, I'm happy with that answer. I haven't gone through that. Like, you know, we have discussed, I spent in 2022, the year I'm recording this, I spent a full lesson just a couple of weeks ago talking about engineering management. It's covered in pretty much every topic, but we talked about specifically the difference between, say, design managers and production managers or site managers in construction. And we talked about a lot of different things. We talked about safety, we talked about labor and resources. The big thing to remember, and this is something I recorded in a trial that I did just maybe a day or two ago, is that if you have a safety accident, if you have an environmental incident, you will not be able to be efficient with your labor and resources. So these sorts of things are kind of encapsulated by the idea of efficiency. So anyway, I'll keep moving. What are we looking at? Next one. Okay, so we have the pulley shown has a mechanical advantage of 4. Now, I don't like this question as much as I would. These days, I would have written that question as the pulley shown has a velocity ratio of 4. We can't determine the mechanical advantage of a device looking at it. We have to measure the forces, the relative forces. The velocity ratio we can tell. So I always like to think of velocity ratio being kind of like a virtual reality thing. It's something that we can it's not achievable in real life. It's unrealistic. However, if they don't say otherwise, we can always assume that things are 100% efficient, in which case mechanical advantage and velocity ratio are the same. So if we go back to Eureka, and I think we go here for Eureka. Okay, so we've got some different pulleys, and we're talking about the velocity ratios of a single fixed pulley does not provide any velocity ratio. A movable pulley does. So what we can do is we can count the ropes attached to the movable pulley. So we have 2. Here we have 3. 1, 2, 3. Here we have 4 ropes that are attached to moving pulleys, and we can use that. So I have. That's not a very good picture. I have some links to Khan Academy. We have the names of these different things. Again, the picture's not very high resolution. I should go back and find that. Here we'd have a pulley with a velocity ratio of 4, 1, 2, 3, 4. It looks a little bit different because this one is changing the angle, whereas this one you're pulling up to achieve it. If we keep going, we should have actually had somewhere, here we go, mechanical advantage. Here we're going to look at levers in a second. The mechanical advantage of the difference between mechanical advantage and velocity ratio. The idea that levers typically are more efficient than inclined planes because of friction. And then in the subsequent, I think it's episode 14, they talk about pulleys and they compare a single fixed pulley versus a movable pulley. Okay. Suck, squeeze, bang, blow. So intake is suck, compression is squeeze, power is bang, and exhaust is blow. I put this in a test, and then my mentor at the time, he said that you probably don't want to have these sorts of questions in year 11, even though I see them in year 11 tests fairly regularly. It's in the Copeland textbook. I'm not going to find it, but it is in there. This is in there, but it's really it is something that we can ask in year 12, because when we do jet engines, it's part of when we do piston engines, it's part of propulsion in aircraft. So I think it's still worthwhile. I teach this in year 9, so most of my students are usually okay with this. If we keep going, I have stress equals force over area. So I talk about the 3 things you need to know to not embarrass me. The first is that concrete is made of cement and aggregates. The second is that stress equals force over area. And the third is that mild steel contains 0.3% carbon and has a yield stress over 300 megapascals. Okay, typically I always say that if you're given areas in millimeters squared, then we want to remember we go together like megapascals and millimeters squared. And the main reason why that's really important is in year 12 we're going to use millimeters to the power of 4, which is some 4D stuff, and it's a bit trippy, and it's this conversion here. Well, okay, that makes sense, but when you're getting to 4D, it's a little bit more confusing, and I just find it's easier if they give us diameters or dimensions in millimeters, especially in millimeters squared or millimeters to the power of 4. We want to do everything in millimeters, and if we know this relationship, what I call the Grease units, because that song is based on the song from Grease, then it might help you out. Okay, so the next thing is we're going to find the vertical component. We're just breaking up vectors. It's pretty easy. This is the stuff that if you do physics, you should be pretty familiar with. Where were we? Oh, okay. So suck, squeeze, bang, blow. I also have like 2-stroke, 4-stroke engines. I wonder what's going on here. The efficiency of the relative temperatures that the different things combust, the flash point. That's not really relevant. None of this stuff is really all that accessible in year 11. Okay, so what we're looking at is stress over area. I said is something you need to know to not embarrass me. I have my under pressure that I made and with a supercut of Pascal from Tangled. I talk a bit about the guy Blaise Pascal and so his philosophy and his mathematics, and all of this stuff it can be found in this video. Prelim Part 3 brakes, or Prelim Chapter 3 brakes Part 2 mechanics. And here we have the idea that 1 Pascal equals 1 Newton divided by 1 meter squared. But with grease units, we can say we go together like megapascals and millimeters squared. You'll also notice the third thing I said here, that steel has a strength measured as 300 megapascals. Anyway, moving on to vectors. Oh yeah, we're going to break these things into, break this diagonal into its horizontal and vertical component. And I've got some older videos there. I actually have an entire playlist now dedicated to that. Where is that? I had that ready. Well, here we go. So an entire playlist with a heap of videos, 1, 2, 3, 4, 5, 6, and then we go into moments. But There are a lot. There's the two videos on vectors. They're at the bottom because I'm not as proud of those videos as I used to be. I have two vector addition questions here. It's like 30 minutes. A vector addition. If you're not sure, check that one out. But we're going to move on. Well, before we move on, I just talk about the disco number. So the idea is that we often are given triangles that are 30-60 triangles. And if that's the case, we can know that the long side is twice as big as the short side. So if the long side is 100%, well, yeah, the long side is twice as big as the short side. Or another way of saying it is that 100% is the long side and then the short side is 50%. Well, the medium size is what I call the disco number, 86.6. Okay, moving on. So we've got a fun question. Now there's different fun questions, friction questions. So friction relies on three concepts. The friction force is equal to the coefficient of friction multiplied by the normal force. And so that's the friction is equal to the coefficient of friction multiplied by the normal. If we're on a flat surface, the normal is equal to the weight, or mg. So mg. Now we have, so the coefficient of friction is equal to the reaction of the force versus divided by the reaction of the normal. We have the normal reaction is always perpendicular to the slope. There's a thing called the angle of repose. You could get that in year 11, but unlikely. I do a demonstration with usually a shoe. But I also, in year 12, we're going to learn about the bear and the box, and then we'll learn about boat questions. And there's also bull questions, which I don't really like. But we're not at that stage. We're just at the pretty simple, not even really sliding. We're just, so the idea of normal force as being perpendicular doesn't really matter when we're talking about year 11 stuff. The question will just be the normal force, N, is just going to equal the weight, or mg. So it's pretty easy questions. I call these ones boring questions. Year 11 questions are boring. Okay, so next we've got strain. So we looked before about stress strain diagrams, and what we can, it's a pretty easy question. So strain is equal to extension over length, or more accurately, the change in length divided by the original length. Just make sure that the biggest thing that people get wrong with these questions is that they use, when we're converting meters and millimeters, make sure that you use them in the right order. And strain doesn't have any unit. It's a percentage. It's a unitless number. Okay. Velocity ratio, we just spent some time talking about velocity ratio. We said that velocity ratios are calculated. We can look at them based on dimensions. And the trick for this question is that we always measure to the fulcrum. So it's 600, I've used meters because I said we should always try and use base units except for millimeters squared and megapascals. So we're 600 away from, this effort is 600 away from the fulcrum. And the load, well, some people would write 13. Oh, and that'd be wrong. The load is actually 19 millimeters away from the, so this is equal to 19.6 plus 1.3 is 1.9, nearly 2 meters away. And that's, people get tricked when we're talking about second and third order levers. People get confused. So don't be someone who gets tricked. Okay, so here we have a nice easy first order lever, and we're going to find the moment forces. It's a pretty easy moment question as far as moment questions go. The idea is that although fat kids always win at seesaw, they don't if they sit closer to, or if they sit closer to the fulcrum. So what we're going to find out is that although this person, or whatever, this 75 kilogram under human earth gravity, versus say their 20 kilo child, if they want to balance out, well, they could slide forward. How close would they be? Well, if the kid is sitting 1.3 meters away, they might sit and only be 0.3 meters away. Okay, so most people are okay with that. If you're not sure about that, again, I have a playlist dedicated to moments. All of that stuff is on here, and that starts where we talk about moments, levers, 30-minute video talking about that. Okay, now the next thing we're going to do is find the reaction. Well, the idea is that unless this thing is falling into the ground, there's going to be a balance of downward force to upward force. So if there's 750 newtons going down, well, the reaction, the fulcrum is going to have to be pushing up 950 in order to keep the thing fixed and not, falling to the ground. Hardness is the resistance to scratching, or abrasion is the better term, impact or indentation. Most people are pretty good at that. That's a pretty common one. The properties, the process of reheating quenched. We talk about testing, and I've talked about, say, the Rockwell hardness test, my nemesis Sam Rockwell, and the other tests like Vickers and the thin metals, the Catfud, and Brunel, which is from the before time, and the Shaw-D test, which is portable. Okay, the process of reheating quenched steels is called tempering. Again, we have our work hardening notes. So we've already talked about tempering a fair bit. That was tempering. Okay, and then biomedical engineering. This is stuff I've done fairly recently. So where have we talked about that? So we talked about efficiency, mechanical advantage, and velocity ratio. We've talked about these guys with their levers. We've talked about the moments. Moment equals perpendicular force. I make a big song and dance about moments when we first start teaching moments, because I think it's a pretty big deal. It's, I think, the most important part of the engineering course. So I kind of talk it up when it starts. I play the song that says, "This is the moment that we learn about moments." Whoops. Okay, so biomedical scope and history. We talk about, so identify some safety considerations, identify some ethical considerations. Probably the one that most people talk about is the guy who talks about getting a surgery to remove his son's cochlears. Brakes. We talk about regenerative brakes and anti-lock brakes. So this stuff, I recorded a video recently. So I had some notes on Facebook where I was just linking to things, but I recorded a video. It's a 30-minute video where I talk about regenerative brakes. Here, what did I talk about first? I talk about ABS first, and then I talk about regenerative brakes second. And then ABS, we have this video, pretty good video. I talk about how I nearly died driving home from Canberra. Grey cast iron, and then I talk about the game TIE Fighter. Okay, so if you go to my notes on ferrous metals, I have two videos that accompany these worksheets. They probably need to be updated. But I have a blank worksheet and I have the teacher answers. We'll look at the teacher answers, and we're going to look at different kinds of cast iron. I say that you only need to know 2 to 4 things about cast iron. The first thing is that cast iron has a lot of carbon. How much carbon? Between 2 and 4% carbon. The second thing you need to know is that it has very good compressive strength, but not very good tensile strength. The third thing is that it has vibration dampening, and the fourth thing is that it has good machinability. And so here we have good machinability and vibration dampening. That's a pretty hard question. I don't think I mean, for 1 mark, that's pretty hard. I'm amazed I gave that 1 mark. I would make that 2 now. I think I probably would have been acceptable. I guess the thing is I have multiple choice, multiple things. You said silicon is used to create graphite. That's fine. If you said that it has good machinability, or if you said grey cast iron has, I don't remember what the actual wording of the question is now. Anyway, I probably wouldn't have, I don't really ask questions about cast iron at all anymore. Just not in the HSC very often. It's really focus, it's a year 11 focus, and I made those videos so that I could say that I've taught cast iron and move on with my life. Okay, so we're doing another moments question. Like I said, they're a pretty big deal. I think we look at exactly this sort of question in Copeland's textbook, so there'll be something on this in that playlist that I showed you earlier. Okay, we've got another thing on, so here we've got pulleys and mechanical advantage. We're going to assume that this thing is 100% efficient, and we've said that we're looking at this thing, we can see it's got 3 different ropes. So if it's got 3 different ropes, it's got, I think in the question it just says a pulley has a mechanical advantage of 3. Calculate the, so I actually did tell you the mechanical advantage, I didn't show you the pulley. And I said this pulley has a mechanical advantage of 3. Calculate the force required to lift 830 newtons, or I think I said 83 kilograms. And yeah, that's pretty easy. So most people remember that mechanical advantage equals load over effort. Remember, the effort is always where the human or the engine is being applying things. Okay, mechanics. So here we have three concurrent force, or 3-force method. I don't think I've ever seen a student use the 3-force method to solve this, but I will just say that it exists. I have in that playlist that we talked about earlier. Here is the 3-force method question out of the textbook. Then I have a couple of other ones where they're labeled with 3FM. So I've got a trial and another trial. So, not many people are, using the 3-force method. I consider 3-force method to be like a really fancy tool that is, when you have it, it's great to use, but you don't really need it. You can make do without it. It's like having, let's say you had an egg cooker, right? I mean, not many people need an egg cooker. Most people can just cook their eggs in a pot. If you're someone who really wants to cook a lot of eggs, then having an egg cooker is great, but most people can get away without it, and 3-force method is that. So most people solve this question instead by converting the diagonal into a horizontal and vertical component. And so here we've said that because this is, I'm not going to go through too much through the trigonometry. I kind of glossed over the trigonometry on the earlier question about breaking things into components. I expect at this point that if you don't know how to find the components of a force, that you will have let me know by now, and that we've gone on Maths Online or done some other remediation to get you back up to speed. But let's say you're in this situation. So what we need to know is that if it's adjacent, this one's adjacent to the angle, you're going to use the force 650 cos 30, and if it's opposite to the angle, it's 650 sine 30. So that gives us our values. And just try to remember the idea that because it's 30 degrees, we know that the small side is half the size of the big size. So if this is 650, then that's going to be 3 something, and this one's going to be in between those two numbers. So that looks reasonable. And if we just take these dimensions off the drawing, we can multiply those forces by the distances, and that looks like this. We've said clockwise is positive. I always use clockwise as positive. We're taking moments about r. And by taking moments about r, we're going to say this thing is going anti-clockwise. The t is going clockwise. And this force of 325, well, it's in line with the r, or it is in reality. I sort of moved it out of the way just to make things clearer. But so it's multiplied by 0, so we can ignore that. That just disappears. Okay, so one part for the trigonometry, or providing the moment equation with some data from the question. Always just write something in here, even if you just kind of made up numbers. I would still probably give you 1 mark for writing something in. Some of the moments about r, well, that might get you a mark. That might get you a mark, depending. Probably not, but hey, better to write that than nothing. Okay, so next we have Pascal's principle. Where do I have notes on Pascal's principle? Here we go. Okay, so we learned about Pascal's principle when we did the brakes report, and we can see here, so we have the brake pedal. The brake pedal is going to push on a master cylinder, and Copeland has a question that looks like this. And so this is exercise 3.8. And these days what I do is I just compare, I say, well, what's the diameter ratio? So the diameter ratio is, the original diameter is 15 to 60. So that's a diameter ratio of 1 to 4. The area ratio will be 1 squared to 4 squared, which is 1 to 16. So that means if we have a force of 400 in the small, we're going to have 400 times 16 on the big. In this case, they've given us the big one, so it means we have a smaller number coming out here. Now you can do this, Copeland would do it this way. He would calculate the areas and then use the areas to use force over area. And when you know the pressure, so the idea we need to know is that Pascal's principle is that a sealed container has the same pressure in both A and B. That's the thing we're looking at. Whereas how I would write that now is I would say I saw this in the answers in a trial somewhere, and I thought, oh, that's a pretty good notation. I'm going to use this now. So velocity ratio is equal to big diameter squared divided by little diameter squared. And I've written the A and B just to make that big diameter and little diameter clear. So if we just take those numbers, we get a velocity ratio of 2.9. If they give us the area, right, which they haven't, but sometimes I do give the area to be generous. I try not to test people twice on calculating areas of circles. I think that. So I just had a power outage. So the circuit breaker just prevented a fire from going off in my daughter's bedroom, so it's good. A bit irritating, but I didn't lose the rest of my recording, so I'm pretty pleased. So I was just saying that, yeah, I try not to assess you twice. So in this case, we're finding the 60 squared divided by 35 squared gives a velocity ratio of nearly 2.9. And then once we know the velocity ratio, we can say, well, 800 divided by that velocity ratio gives us 272. And yeah, it's probably 1 mark for each of those things. The next thing we're going to talk about is communication. It's asked you to draw the third angle projection symbol. And I will go to our notes. Sorry, some things may have to reload. Okay, so in our drawing resources, I have the VCE standards. Sorry, again. I talked about all of this stuff way back in chapter 1 when we were doing communications in the communications textbook. But the thing about drawings is it's always a bit hard to know how much detail to give in each chapter. But by year 11, we should be pretty familiar with the stuff in this VCE book. Even though it's for Victoria, it's got some good stuff in there. And specifically, I did have the page ready. Yeah, okay. So it's talking about how to draw third angle projection drawings. In Australia, that's what we're supposed to do. And then it's got the symbol here. Now, that's a better symbol than my symbol, but I drew this before I knew this book existed, I'm guessing. And the idea is that in Australia, we draw the top view on top. The top view is always directly in front of the front view. You can see how all of these views line up. So nothing is off to the side. I had a student who was doing a practice test today, and my advice to him was make sure that everything lines up. So for this question, what we're going to be, let's see what I've got next. I'll click on these things just to give them a chance to load. Okay, logic gates. Yeah, okay. Sorry about that. Okay, so the idea is that all of our stuff lines up. So the top view is on top. It directly lines up. So, okay, what are we getting marks for? Well, first of all, you get a mark for drawing something. As long as you don't draw a smiley face, if you made a reasonable attempt, if you just redrew and traced that object, well, I'd probably give you a mark for that. Okay, so the first thing is generally, is the thing, more or less, does it look right? 1 mark, and maybe even 2 marks for just looking right. Depending on in HSE, you might only get 2 marks for just looking right. The next thing is line quality. Now, if you want to use a ruler, I drew these ones with a ruler, but you can see my videos online where I do a lot of drawings just freehand. I'm pretty good at freehand drawing, but I've been doing this for a long time. By all means, you're allowed to use a ruler and a compass, but if you want to freehand as well, what you can't do is feathered lines, and especially early on I make a point on this. So for drawings like the drawing task 1 to 5, I talk about this a lot. The next thing is orthogonal. So the idea is orthogonal is you get a point for making sure that everything lines up, that the top view is directly on top and that the front view lines up with the side views. The next one is I asked you to draw 1 dimension, and the dimension had to be written above the line. Probably the arrow is part of that as well. Then I have line types that you've included a hidden detail line. I asked for a hidden detail line here. I asked for a center line, which is this thing here, and the idea of third angle projection, which I've already mentioned, top view on top. So to be honest, when I first started, my mentor sort of broke things up into like thirds of a mark. And I found that very difficult. Whereas my experience HSC marking now is that it's just holistic. The markers have a general sense of what 1 is and what 6 is, and we go from there. But that's it. I'm usually able to defend. I've never struggled to defend the marks I give when students come up. I always, if you feel as they haven't been marked fairly, please let me know and I will talk to you. Okay, so then we're going to draw a pictorial drawing. Now we can draw this as either isometric. I've chosen oblique because this only has one circle, and when there's only one circle, it's a whole lot easier to use oblique. I effectively just drew the front view, right, and then I moved this line forward and I moved that line back. So I talked again about line quality, so drawing just neat lines is really what I'm looking for. I don't mind if they're freehand as long as they're neat. No additional or missing lines, so like forgetting this might be an example, or not drawing anything else. You'll notice that I've got my construction lines. That's a-okay. You won't lose any marks for construction lines. No need to rub them out. Just make sure that we can tell the difference between what is a construction line and what's not. And then correct view dimension. So it did tell us to look from this angle, or there was an arrow saying from this angle. So it's important that you could lose a mark for drawing from the wrong angle. You might not in the HSC, you might not. Drawings are done so badly in the HSC that they mark very generously. Okay, getting close to the end, we've got an AND gate. Just draw an AND gate. Now, some people just drew 2 open switches, and I get that. That is an interpretation. I probably wouldn't be as vague when, but if we're just drawing the symbol, the logic gate that represents an AND gate, well, that is given in the it's given in the formula sheet. So pretty easy. All you need to do is copy that one. Okay, so we've got annealed 0.6% carbon steel. What does that look like? Well, it's got more pearlite than it otherwise might. It's got more than half pearlite. So pearlite is the layered or lamellar layers of ferrite and cementite. And then because it's less than 0.8, anything less than 0.83, what we call the Punzet number, it's going to contain ferrite. Where did we talk about this? So let me get my notes up again. Yeah, this could be a tough one. Okay, so when we talked about heat treatment, I know that's all about work hardening. So I do have this somewhere else though. Hopefully I haven't closed it. When we're talking about ferrous metals. Okay, so hypoeutectoid means that it's got less than 0.83%. So it's got this as ferrite, whereas hypoeutectoid is when we're past 80%. And the difference is here we have grains that sort of are their own free ferrite grains, whereas when we get past 8%, 0.83%, we're going to get these little rivers of cementite. And it's important to remember that the cementite is actually silver. That what we can see is the grain boundaries. There was a question in a recent trial that kind of indicated that the dark ones were cementite. I didn't like that. Anyway, so where do we see that? If we look in our ferrous metals notes, we can see that it's on figure 3.11, hypoeutectoid, and if we're looking at okay, we're also asking for annealed. Because it's annealed, it means large grains, big equiax grains. It's always hard to tell if something's big equiax grains or not. If we go back to the thing we were just looking at. So the difference between small grains and large grains, we can tell here because they actually have a scale that references them, but generally without looking at them side by side, it's hard to tell. Okay, moving on. How do we anneal? Well, first we heat to red hot, then or above the recrystallization temperature, in this case over 900 degrees, and then we cool slowly in a furnace. So we always say aloha to anneal when we talk about annealing. We've got Roku with his furnace of the gods, a volcano, and we cool slowly in that furnace, and then we have low stress, big, soft equiax grains. Okay, The grain structure of a forged stem will follow its shape. Why do we do this? Because it has less points of weakness. This is in the Copeland textbook. I don't have the with that power outage, I don't have the textbook anymore, but I've put this in every test for 7 years. Who knows, this year could be time for a change. Probably not, but you never know. So yeah, it's a pretty good one. We like to talk about forging. Yeah, we'll just grain flow. So here's some typical pictures that we often see of the flow around forged parts. And this reduces the points of weakness that we would have if it was machined. So we can see here that the grains have flowed around the object, whereas if the part was machined, we'd have points of weakness, and it'd be very easy for that part to be broken out. Okay, lastly, so we've got some casting. So if we go to casting, I have a whole thing on logic gates. I went a bit logic gate crazy a couple of weeks ago. In terms of the hip stem, I expect people to know a lot more about artificial hips than, say, other things, and that's because I say like the artificial heart, and part of that is because I set a task for the last 2 weeks. I've been given people a task to work on an engineering report. Now I say you should only spend 6 hours on this task. You should work with a friend. I have a sample task that you can plagiarize fairly heavily. It's not an accessible task. I mean, so I'm saying plagiarize a little bit tongue-in-cheek, but the point is I've given you all the topics, I've given you the headings, I've given you even a sample report. I thought I gave you a sample report. I thought I put up a blank one. I'll have to have a look at that. Anyway, okay. Next, we're talking about casting. Yeah, so casting, we'll come back on, that's two sides here, riser and investment casting. So I have a video I'm pretty pleased with on casting. It's a 50-minute video on casting. It covers both the 11 and 12 content. Here are the questions I've asked intermediate, like through that. Do I talk about runners and risers? Yep, compare the runner and riser. And what are the 4 stages of investment casting? So pretty common questions I like to ask. Now normally we only give full marks in exams, but I just want to give you the idea that there's 4 parts, so I'm trying to break it into 4 parts. I probably should have just done dot points. That would have been smarter. Anyway, moving on. Okay, lastly we're going to finish with aluminium, the properties of aluminium. And what I had is my the notes that I handed out right at the start of term 1. Yeah, I guess I'll pause for a second. Okay, so blink and you'll miss it, but of the 40 pages, I've got about half a page on non-ferrous metals. And that's probably all we really need to know in year 11. We talk about copper alloys and aluminium alloys. I've asked you to identify 2 advantages of aluminium, and that's pretty much all I need. So we talk about it being lightweight, and we talk about it being corrosion resistant. That's really what we're looking at. A more correct term is high specific strength, or high strength to weight ratio. But corrosion resistance, we talk about aluminium having a passive oxide layer, which means that even when it does corrode, when it oxidizes, it doesn't rust the same way that steel does. We did talk about timeline of, so it's a fairly easy bit of homework where I said, read these 4 pages of the Copeland textbook where we look at the history of lawnmowers, and I've asked identify 4 innovations. That's not really specific to this question though. This is more an understanding of it's applying your knowledge of aluminium to think about why we would choose aluminium in the lawnmowers. This is probably the extent of what we'd ask you about aluminium in the Year 11 course. In Year 12, we do talk about aluminium much more extensively. I'll quickly get one. Okay, I'm back. So when we learn about aluminium, there are aluminium alloys can be classified by a 4-digit number, and some of them are heat treatable. We will learn about the form of heat treatment called precipitation hardening. This video here does a pretty good job. Real Engineering does a pretty good job talking about precipitation hardening. But for the moment, we don't really need to know that much about aluminium alloys and their applications. Just light, and we also should know it's a good conductor of electricity. That's the other thing you should know. Hopefully this video has been of some help to you.